Okay, hello everyone. Nice to meet you all. It would be nicer if we meet in the class. However, because of the coronavirus, unfortunately, we are meeting online. Sorry for that. But anyway, nice to meet you all. Okay, before we start this introduction to mathematical statistics, let me introduce about myself a little bit. And I am Ilyop Kwak, and I am an assistant professor in the Department of Applied Statistics at Chungang University. And my research interest is AI security and statistical genetics. And I am eager to design new methods for big and complicated data. And I like to play with data sets, and I like to make some statistical methods on the data. And I am also excited to develop new usable tools for the method so that those methods can be widely adopted and used by other researchers. These are my interests. And okay, and uh, how many of you have seen this photo book? Actually, if this is a classroom, probably I can see how many of you have seen this type of photo books, but unfortunately, I'm just guessing. Probably few of you have seen this photo book of your parents, or maybe your grandmother or grandfathers. I don't know. But as time goes, the we are storing our pictures in digital storage as file, like um, JPG files, and even more, we are storing our photos in the cloud. Uh, and here's example of Google Photos. And what I'd like to say is that the data, the how we save the data, the trend is changing like this. In early 1996, there's only few of digital storages available. In these days, the analog data sets are prevalent, like paper, film, audio tape, and many of them is stored in analog storage. However, as time goes, many of these are stored in the digital storage. So after about 2002, it's beginning of the digital age. About more than 50% of data now stored in digital storage after 2002, and actually it's getting faster and faster. And nowadays, about 94% of datasets are saved in digital storage. Okay, what this implies. So, as time goes, computers are getting faster and faster, and information storage is also growing bigger and bigger. So is the data. Is data in the digitalized data is getting more and more. And what this means that it opened big data era. So it's not only for statistics, it's about the all areas like computer science, economics, biological science. In all the fields, they talk about big data because there are more and more data sets in every field. So it opens like IoT era, internet internet connected to every devices, IoT, and also this is 5G at the era of 5G, and there will be 6G in the future. And also, as we have this big data ecosystem, we are talking about AI. It's like how can we utilize this big data? How that's the AI thing. And what's next? So we have big data, and we this is a good ecosystem for AI. And what's next? The next thing is the growing need for the data scientist. So we have big data, and this is good ecosystem for AI. So we need more people for the data analyst, which is data scientist. So in the United States, data scientist is the top job for like um, 3 years in a row. So this is probably the most sexist job these days. Um, and especially for 2019, the three of the top five jobs are in the data analytics field. The number one was data scientist, number three was data engineer, and number five is analytics manager. Okay, and and the core skill set for data scientist is like that. This so for the data scientist, we need the skills for the math and statistics, and also skills for IT, computer science and IT, and also the domain knowledge, because data scientists work at a bank, or sometimes IT companies, or sometimes in biomedical sciences. So that's domain knowledge for that specific areas. Okay, and let's talk about your dreams. What is your dream? Why you come to statistics department? Probably you'd like to become a data analyst, or you'd like to work in the company like bank or IT companies or biomedical companies or survey companies or anyway you would have your own dream. And I think this mathematical statistics course could be one of the core skills for your dream. So I think this is a pretty important class for your future. And and yeah, so our objective of this class is to learn the mathematical background for the statistics by studying the materials in the mathematical statistics class. Okay, what you are going to learn through this class. So in chapter 2, you are going to learn some basic probability, and in chapter 3, you are going to learn discrete random variables, the probability distribution for discrete events, just like flipping coins or rolling dices and etc. And in chapter 4, we were going to learn about continuous random variables, such as your height or weight, distribution of height, weight, or distribution of our salaries, our incomes, or our scores, or something like that. And in chapter 5, we are going to learn about multivariate probability distributions, and which is the when we have multiple number of variables. We are interested in the distribution of multivariable uh, uh, things. And in chapter 6, we are interested in functions of random variables. And why is it? Actually, most of times we are interested in function of random variables, not just random variables. So let's think about this game. You are getting $10 if you get head of your flipping coin. So if you flip coin, if you have head, you get $10, and uh, if you get tail, you get $5. Then what would be the expected income of that game? That in that case, probably you need function. Or let's say that your random variable, it's one for head and -1 for tail. Then you need some function to convert that one to $10 and -1 to $5, and then calculate the income, something like that. So this is functions of random variable. And in chapter 7, we were going to learn about sampling distribution and the central limit theorem. And in statistics, we are interested in the population. And actually, it is impossible to uh, look at all the populations. So in statistics, we just sample some of them and uh, do some reasoning on that sample. So we need sampling distribution, and we will also talk about the limiting distribution of that, which is the central limit theorem. And this is how I will cover the the, the mathematical statistics 1 course. And yeah, and the next thing is how we study. How we study. If you would like to uh, do good performance on this class, what's the strategy? And I recommend you to solve and understand all the problems in the textbook and also in the homeworks. Actually, homework problems are from the textbook problems. So if you, I recommend you to solve and understand all the problems in the textbook, then I think you don't have much problems when you are solving midterm and final term exams, because I'm going to uh, I think probably most of my exam questions will be from homeworks or textbooks, so with just slight modifications. So um, if you study all the problems in the textbook, and there would be not much problem, I think. Okay, and then I will start the section 1 of the textbook, which is introduction section. And in section 1.1, this is talk about what is statistics. So what is statistics? Probably I would ask questions if this is in class, but since it's online, I'll just say that statistics is a theory of information with inference making as its objective. So statistics is about theory of information and inference making. Our objective is inference making, and to do that, let's look at this. The large body of data that is the target of our interest is called the population. So population is the target of our interest, and the subset selected from it is a sample. So to do the inference on the whole set, the population, we select the subset sample from the population, and we do inference making on this uh, on the using the sample, and we do inference making about the whole population. This is the um, statisticians doing, and okay. And this is an example estimating preferences of voters. The preferences of voters for a national candidate Jones expressed in quantitative form, 1 for prefer and 0 for do not prefer, provided a real finite value. And we are interested in the true fraction who favor his election. This guy Jones is running on an election, and we'd like to survey about his how many people prefer um, he win, or how many people do not prefer he win, something like that. In addition to the estimate itself, Jones should also be concerned with the likelihood that the estimate provided is close to the true fraction of eligible voters who favor his election. So he have two interests. The first one is true fraction. How many fractional people favor elected. Uh, and the next question is, how reliable is that fraction? So you get the estimate. Um, the true fraction for Jones may be zero point 0.3. However, you get the estimated fraction, maybe probably zero point 0.4 or something. Then we would probably are interested the likelihood of your estimate is close to the true fraction or something like that. And in statistics, we do this kind of inference. Um, so the objective of statistics is to make an inference about a population based on information contained in a sample from that population. And second, to provide an associated measure of goodness, how reliable it is, and something like that for the inference. Okay, and uh, and in this chapter talk about characterizing measurement and graphical method. Characterizations processes practical significance so that knowledge of the descriptive measures for a population can be used to solve a practical non-statistical problems. So these characterization processes for some descriptive measures. Actually, let's look at the example. Example is to characterize the 10 measurements, these 10 numbers, and can be characterized by a relative frequency distribution like below. So for the values between 2.05 and 2.25, uh, oops, so here 2.1 is here, and also, uh, oh yeah, here 2.2, 2.2 and 2.1 are in this region, so the frequency is 2, and probably there's three values inside here, 2.4, 2.3, and 2.4. There are three values in this range, and and so on. So this frequency table, a frequency graph, shows the relative frequency for the given characteristics, and and in statistics, we many times we like to assume that the data follows the normal distribution. So in this case, we can estimate the mean value of these 10 measurements, and also we can estimate the variance. And by using those two estimates, we can estimate the data distribution using normal distribution. Probably we were going to cover more details in the future lectures, so don't worry if you don't know much about even about mean variance or normal distribution things. It will be covered in the following lectures. And character if and for characterizing measurement with numerical method, here's the most common measure of central tendency, the mean of a sample of n measured responses. If there are y1 to yn number of measured responses, the mean of a sample, the central tendency, can be represented as um, summing every responses and then divide it by n, and you can have the most common measurement for central tendency, and we call it mean. And the corresponding population mean is denoted as mu. Um, so the symbol y bar, you can read this symbol as y bar, refers to a sample mean, and this sample mean we do inference for the population mean. We usually denote it as mu. So this mu is the population mean, usually we don't know the exact um, value of this mu, and to do some inference about this mu, we usually calculate mean, the sample mean from the subset of the whole population, and this is y bar, average of all the measurements in the subset. uh, yeah, okay. And and if you have the mean, um, we are also interested in the variability. Let's look at these two figures. The first one and the second one. In these two, in for those two cases, they have same mean for distribution 1 and distribution 2. However, the variability is very different. For this case, the variability is uh, comparably smaller than this one. So we may need a descriptive measure for the variability, and how we can define this kind of variability. The most common measure is the variance. The variance of a sample of measures y1 to yn is the sum of the square of the differences between the measurement and their mean. So here, their measurement and their mean difference, and we do the squared sum of them, and then divide by n minus 1, and we call it the sample variance. And probably some of you are wondering why this is n minus 1, not n. And actually, the reason will be covered in the following lectures, so wait until that. I will explain it later, so don't worry about that. And the corresponding population variance is denoted by the denoted by the symbol sigma square. This is the corresponding population variance, and to estimate this population variance, we use this sample variance to estimate this true population variance. And since this variance term is squaring our measurement, so if the unit of our measurement is centimeter, and then the resulting measure of these is centimeter square, so many times the standard deviation is also widely used to normalize the unit. If the unit is centimeter square, we'd like to get the normalized one, which is a centimeter. To do that, we just get the square root. So standard deviation s is square root of s square, and the corresponding population standard deviation is denoted by sigma, which is square root of sigma square. Okay, and and okay, and for a distribution of measurements, many times we assume that normal distribution on the data, and if that normal assumption is true, what we can say is that the mu plus minus 1 standard deviation, 1 sigma, contains approximated 68% of the measurement. So here in this area, 68% of data sets are inside this range. And for mu plus minus 2 sigma, so mu plus minus 2 sigma, it contains about 95.4% of data sets. And with mu plus minus 3 sigma, it contains almost all the measurement, which is 99.7% of datasets are inside of this range. So we can do inference like these if we assume the normal distribution on our data. Okay. So subchapter 1.4, it's about how inferences are made. And to explain how inferences are made, there's an example. Would Jones can be elected? In previous example, Jones is going to so here, let's read it. Suppose that two candidates are running for a public office in our community, and that we wish to determine whether our candidate Jones is favored to win. So, so we are interested in whether Jones is elected, whether Jones is favored by people. So we went to do that, we randomly select a sample of 20 from all voter pools. And let's say in our 20 voter samples, uh, all 20 voters said they were going to vote for Jones. Wow. And assume that the probability for voting Jones is actually this is null assumption. Okay, let's go back here. All 20 voters said they will vote for Jones. So how do you think? Um, Actually, there's very high chance of Jones will be elected from this result. And and in statistics, how we reason for this um, in probabilistic way. So the first thing that is we assume that um, so if the probability of voting for Jones is over than zero point 0.5, Jones going to win. So in the null hypothesis, in null hypothesis, we assume that the probability for voting Jones is zero point 0.5, and with this null probability, observing all 20 voters support Jones is highly unlikely. So under the assumption of this probability for voting Jones is zero point 0.5. So um, so because of these, we reject the null assumption. We think that this null assumption is not true, and then if the null assumption that probability for voting Jones is less than zero point 0.5, then the other assumption would be true. The probability for voting Jones for all voters is much higher than it is highly likely that Jones will be elected. This is how reasonings are made in statistics, and actually this kind of hypothetical inferences will be covered in mathematical statistics too. Okay, and also here's another example: A/B testing in IT companies. So let's say these two designs are from Google, and Google designer designed these two designs. Which design do you prefer? How many of you prefer this, and how many of you prefer that? Actually, if this is anyway, um, so is there a way that I can determine uh, which design is better in using statistical testing? Any ideas? Probably you pause this and then think about it, and I can tell you. For these two web pages, we randomly submit this page for 500 people, and we randomly assign this design to another 500 people, and we can count the number of Chrome downloads from these 500 people and these 500 people. I say that, let's say if 20 people downloaded Chrome from this population and 40 people from this population downloaded the Chrome, then it says that since 40 people is much higher than 20 people, um, by testing whether these differences statistically significant, um, we can take this design from our statistical testing. So this is how inferences are made in statistics and in IT company situation. Okay, and theory and reality. Actually, there is a gap between theory and reality, and in this text, we will study the mathematical theory of statistics, and it can be tied very closely to reality and can be useful in making inferences from data in all fields of science. And that's why we study theory. And okay, thank you very much, everyone, and enjoy studying mathematical statistics. Thank you.